Hello everyone, I'm Yijun Yuan. Here we present indirect point cloud registration, allowing distance fields using a pseudo third point site. As we all know, in this following registration task, SCP is the most universal model. The major cost of SCP lays on nearest neighbor search with its n square, or n log n with the tree structure at each iteration. Many other algorithms with similar citing also cannot significantly avoid the cost. In addition, the ON cost is inevitable since transformation requires at least ON. Yep, can we do it faster? So the other reason that we can do this work is for the multi-map neural-based reconstruction. So we found that there's no such registration between two neural implicits. And the second, transformer PC, the point cloud, then encode is not cost-efficient. And third, transformer neural implicit is much slower than transformer point cloud, which was solved in the paper 3. So we kind of asking ourselves, can we build a registration algorithm that can register two neural implicit maps or distance fields without changing the original process? Can we do more efficient search? So a straightforward idea comes to our mind is to introduce another model to communicate instead of letting them contact directly. Such that transformer point cloud is equivalent to transform the new model in the inverse direction. To make this work, we have to first ensure that we have a function. Transform both point cloud and the third model will not change the feature. And that's what we call transformation invariant. With such a function, registration P to Q is equivalent to transform S in the inverse direction. Here in this paper, we find one such option. There might be more, but will be possible future work. So this function is based on the distance field. As we said, our third model is a point set. Each point basically has a distance value on the distance field of P. Thus, we get a global feature, which is a concatenated distance value of the site. As we said here, we call it global feature of the point cloud, which is a vector. Our method is classified as a feature metric registration, where they are all deep learning models. For the time complexity, our model is O big over K L log n, which is even faster than the feature metric registration. Of course, it's excluding the n log n tree building time. And surely we follow feature metric registration pipeline to write a formula to minimize the distance between two global features. With the incremental twist parameter at iteration I, we rewrite and expand the problems such that a problem is solved with Gaussian-Newton. So here we follow the point night LK revisit to rewrite analytical Jacobian with a chain rule. So on the right side is a feature Jacobian, on the right side is a wrapped Jacobian. The wrapped Jacobian can be easily written, but for the feature Jacobian, we basically only have value on the diagonal, which is like this. So next, we solve J C equals to residual to approach the step transform. So the whole pipeline is running like this. So first we have point cloud P and Q, and we introduce a pseudo site S, and together to encode P and Q to get the feature of Q. And then in each iteration, we gonna transform the pseudo site and get the new feature of P to solve the global feature registration to update the she, which is the twist parameter. We early stop when the delta she is small enough. So above problem is basically solving J she equals to residual in each iterations. So is there a more robust solution? And our answer is that we may consider each pseudo point has different weight because each point are independent. It is supported rewriting the formula to L1 form. Then we can use iterative reweighted least square to solve such a problem in similar form. For which the neural feature-based FMR do not support. So next comes our experiment to demonstrate the performance. Firstly, we compare with traditional and deep learning method on object dataset. You can find that even without any training, our method shows a similar accuracy level to the feature metric method. We threshold the error for success rate. Our method shows even better than 0.9 revisited. Moreover, we test the robustness of our method. We further test sparsity and noise. We find that our method is more robust than the density. However, it is not good on noise. This makes sense because the distance field naturally has big response to outlier points. To make the method more robust to noise requires a filtering of the point before generating the distance field. Then we also make tests on indoor data, 3D match, and outdoor data kitty. On 3D match, our method easily exceeds deep learning method. However, SCP get a good median on translation. When we use truncating to figure out some pseudo points, our method shows best median. On kitty, our model is competitive to other deep learning methods in the outdoor setting, but GSCP shows the best on rotation. To further demonstrate the use on real life, we test frame by frame on kitty odometry square theory. You can find without the loop closure, our trajectory is still very close to the ground truth. So in this paper, we introduce the indirect point cloud registration method using a pseudo point site. We extend the feature metric registration class algorithm to a non-deep learning setting. The pseudo point-based design highly reduces the theoretical time complexity and space complexity. Thank you for your attention.